In this video, we will go through notes 1 through 3 of the acids and bases unit in organic chemistry, and that's unit 4. A lot of this material should be reviewed whether you've taken regular chemistry or AP chemistry, but this is material, especially some material notes 4 that we're going to need moving forward. So, properties of acids and bases. You may know that acids tend to be sour, where bases tend to be bitter. A good example of a common acid would be something like soda. A common basic solution might be something like a soap solution. Soaps are bases. Phenolphthalein is an indicator. Methyl orange is an indicator, and they turn different colors depending on the pH. And then acids, you probably remember acids have low pHs, pHs less than 7, and then bases have pHs greater than 7. And the definition that we're going to use here is that acids donate H plus ions and bases accept those H plus ions. And so if we look here at this reaction, I know that HCl is an acid, and I know that H2O is a base, and water can actually be both acidic or basic depending on what it's mixed with. And here's how I know this. HCl turns into Cl minus, meaning it gave up H plus. That's what makes it an acid, not because it has an H. Okay, because water also has an H. So how does this happen? Well, we would look at pKa values, and this is getting way ahead of where we're at right now, but it'll make some sense maybe. This pKa for HCl is, we're going to learn that it's -7. And then this pKa for water, we're going to learn that it's 15.7. And so things that have lower pKa values are going to be stronger acids. Okay, and so what happens is we're going to learn how to draw arrows where the lone pairs of the electrons in water go and attack the H, but we're really interested in H+, and so the electrons in that bond return to chlorine, and we get something that looks like this. Now, I'm going to erase all of this, and we're going to say, okay, well, these equilibrium arrows say that we can go backwards. And so if we go backwards, chlorine would behave as a base because it's coming in, getting an H, and then giving the electrons back to oxygen. H3O plus 1 hydronium here is donating the H plus, and so it must be acid. But as we have it right now, if we call all of these acids and bases, it gets a little bit confusing. So any sort of product in an acid-base reaction would have the word conjugate in front of it. That way we know that it is a product. Okay, so by definition, an Arrhenius acid is a substance that produces H plus in water, where an Arrhenius base would be something that produces hydroxide ions in water. The most common definition that we're going to use is dealing with Bronsted-Lowry, and that states that acids are proton donors, where bases are proton acceptors. It is important to know that H plus is hydrogen that has lost an electron, and so H plus is the same thing as hydrogen ions. But it's also the same thing as a proton. So all of these are interchangeable, okay? And so throughout this unit, I'm sure I will use each of these many, many times. We have in chemistry a lot of substances that can be called amphoteric, and what that means is that they can accept or donate a proton. There's a lot of amphoteric compounds if you ever take biochemistry. Most things, I would say, in biochemistry can be amphoteric, and we'll learn that when we draw proteins and with amino acids and bond them together. And it really depends on the pH of the solution. Now, one thing that's kind of unique about acids is acids give away or donate one proton at a time. So we could have a monoprotic acid. That would be something that only has one H to give away, like HCl. Or we could be polyprotic, and within polyprotic, there's diprotic, meaning it would be like H2. H2X maybe. And then we also have triprotic, which would be something like H3 and then X, whatever anion that might be. Okay, but even though they have three H's, they don't give them all three away at the same time. They do one at a time. Okay, so what I want you to do is pause the video, and I want you to look at these reactions, and I'm going to go through them very, very quickly, and I want you to label the acid, the base, the conjugate acid, and the conjugate base. Okay, so pause the video here. H2S becomes HS minus, so this will be acid. If it's acid on one side, it will not be acid on the other side. Therefore, we can label the rest of these. HClO4 becomes ClO4 minus 1, so it loses an H, so that becomes conjugate base. This is conjugate acid. Water here becomes hydroxide, so it loses an H. That means that water would be acid. This would be conjugate base. This would be conjugate acid. This would be conjugate base. Carbonate, this should really be CO3 2 minus. That's a mistake on my part. This gains an H, becomes HCO3, so this will be base. This will be conjugate acid. This will be acid. This will be conjugate base. This is CH3COO minus, it gains an H, so this will be base, conjugate acid, acid, conjugate base. And then both of these could be acids. What we'll see though is that water becomes H3O plus 1, it gains an H, so it's a base here, acid, conjugate base, conjugate acid. Okay, now determine the conjugate base for the following acids. If we look at what we've done before, we have acid and we have a conjugate base. So what's the generic pattern? It's a conjugate base will have one less H plus. So we'll get something like the H plus has come off and we'll have HSO4 minus left behind. Notice we're not just losing H, but we're also losing a positive. That's why this becomes HSO4 minus 1. HBr, same thing. And I'm circling the conjugate base. This becomes Br minus. This becomes H plus OH minus. This becomes H plus PO4 3 minus. Okay, so the things that I have circled are the conjugate bases. Okay, now, whether you had this material in regular chemistry or AP chemistry, we're going to go through equilibrium, and I'm calling it baby equilibrium because if you've taken AP chemistry, you know equilibrium is sort of a big topic, and we're going to get into a lot of it, but not all the kind of intense math operations that you might be able to do with equilibrium calculations. So equilibrium is a state where the rate of the forward reaction is equal to the rate of the reverse reaction. When this happens, the reaction is said to have reached equilibrium, and so what's sort of difficult to think about is reactions never actually stop. They just appear to stop because the forward reaction and the reverse reaction are at the same rate. And so I always, in class, I would say something like, imagine you're on the highway and you're driving and you look over and the car next to you appears to not be moving, and that's because you would be at the same rate, but in reality, you are both moving. Okay, so we can mathematically represent an equilibrium reaction using something called K. This is the equilibrium constant, and this is the ratio of products to reactants when the reaction reaches equilibrium. Okay, now what's kind of weird is that solids and liquids are excluded from our equilibrium expression. Okay, and how we do this is we write, okay, we say we have NH3, that's a product, so we write it in brackets. Brackets mean molarity. Okay. We will square it because the coefficient is 2. We'll divide that by the reactants. I check, all of them are gases, so we're good. We don't need to worry. We have N2 to the first power. Its coefficient is 1. We don't need to write that, but it is. And then H2 to the third power because its coefficient is 3. And let's just say we had copper solid. I know we don't, but let's just say we did. We still would not change our K value because copper is a solid and would therefore not be included in our equilibrium expression. Okay. Now, if K is really large, greater than 1, that means products are in my numerator. They must be really big compared to my reactants. This would be called product favored, and this would be a spontaneous reaction. And then if it's reactant favored, that we would still have products, we'd have some, but our reactants we would have way more of. This would be called non-spontaneous, which I like to call non-spawn. Okay, spontaneous does not tell you how quickly a reaction proceeds, but just tells you whether or not the reaction will proceed. Okay, so I want you to pause the video, and I want you to think about how to write the K expressions for A, B, and C here. Okay, so I'm going to go ahead and do that as well. So K is equal to NO2. It may be helpful to check it off once you've put it in your K expression. We have O2 to the third power, and then N2O to the second power. In B, we have K, that's also equal to NO2 here. It's going to be the same exact reaction, but if you notice, my coefficients, I've halved them, so that's a relationship between them. But for oxygen, don't get thrown off. It has a 3/2 coefficient, so it'll be to the power of 3/2, and that's something that we can do. Luckily, we have calculators. Okay, and then in C, it's actually the reverse reaction. And so if you notice, we will actually just take this, we'll copy it, paste it down here, and all that will happen is we'll take these guys, we'll move them to the denominator, take these guys, we'll move them to the numerator, and we actually get the reverse reaction. Okay, and you can see mathematically that's just the reciprocal of our K value in A. Okay, now we're going to do the same thing in question 2. Here, though, we have acid-base reactions, and so I'll show you some things that we have H3O plus. So when H3O plus 1 is produced, we are going to treat that like H plus. And so what that means is if we produce H3O plus or H plus, we'll have a K value, and this K will be H3O plus HS minus 1 divided by H2S. Water is a liquid, so we won't include it. But this, if you produce H3O plus, we're going to learn later in the unit that this would technically be called a Ka expression, an equilibrium constant expression for an acid. Okay, same thing is going to be true in B because I have H3O plus, so I'll say H3O plus. The coefficients for acid bases in an acid-base reaction are almost always 1, so that's kind of nice that we don't have to worry too much about coefficients here. And then again, water is a liquid, so it won't be included. And this part C, this would just be a K expression because we don't have H3O plus produced. If you produce hydroxide, actually, you would use Kb, and we'll get to that later. Okay, so we have Cl minus, HC, oh wait, I wrote that wrong. CH3COOH, HCl, CH3COO minus. Notice I'm not excluding any of them because they're all aqueous. Okay, now we're going to talk about Le Chatelier's principle, and I'm just going to do a couple examples here. This key is posted online so you can check any examples that we don't do. But Le Chatelier's principle states that you already have a reaction at equilibrium. So you're already at equilibrium. You're at your equilibrium constant K, and there is some sort of disturbance. Okay, you disrupt the system, and that messes with your ratio. Okay, so the ratio of K will be disrupted, and the system is going to have to readjust to achieve equilibrium. Okay, so if we increase the concentration of one species, we'll shift away from that species. If we change the pressure, then we're going to go to the side that either goes back to our original pressure. And for the sake of organic chemistry here, I'm going to talk about it, but this is not important in organic chemistry. Okay, and then if we change the temperature, we're going to shift towards the side that restores our temperature back to where it was. So let's see what this looks like. If we add some CO2 here, okay, we can think about the amount of CO2 has now just increased. Our reaction is no longer at equilibrium, so we need to shift away from CO2. The only way this reaction can shift away from CO2 is if it shifts left, because CO2 and calcium oxide would react to decrease the amount of carbon dioxide that we have. Okay, and that would be advantageous for us. If we remove some CO2, now CO2 is not enough, so the reaction needs to produce some more CO2. So this would cause the reaction to shift right, because that would generate more CO2 with the decomposition of calcium carbonate. If we add some CaO, this would go up, and you might say, oh, well, we have too much of that. We need to shift left. And I think you're thinking about this almost right. But what actually happens is no shift, because solids are not included in our K expression. If we increase temperature, I know temperature is not included in our K expression, but our K value is actually only dependent upon temperature. We change temperature, and that changes our K value. If we have too much heat, the reaction needs to consume some heat. If we go left, the reaction will consume some heat in addition to calcium oxide, carbon dioxide. Okay, so we would shift left. If we decrease volume, this will increase our pressure, meaning we need to generate less pressure. And the way we can generate less pressure, that would be the side with less gas moles. Okay, so we would shift away from CO2, that has 1 gas mole. This has 0 gas moles. So the left side gives us less pressure, so we would shift left. And if we add a catalyst, we'll actually talk about catalysts in Unit 5. Catalysts are something that speed up a reaction, but they don't alter how you end up at the what you end up with at the end of your reaction. So you could think about it like if you drive home, maybe that takes you 10 minutes to get home after school. But if you teleported home, that would take you maybe 30 seconds. And so you get home a lot quicker, but you're not going to change your destination. So this would actually be no shift. Okay, so let me go through an example problem, and then I will leave the problems on page 6 for you to do on your own, and then check with the key on Schoology. This whole arrow system here that I'm going to write on, I don't care that you're using that. I just care that you have the correct predictions for shifting. Okay, so PCl3, if we increase that, we will end up shifting right. If we remove some Cl2, we need to generate more, so we will shift left. If we remove some PCl5, we need more of that, so we will shift right. If we decrease the volume of the container, well, that's going to increase pressure, meaning that we need less pressure. This side of the reaction, the left side, has 2 gas moles. This side has 1 gas mole. And so we need to shift to the side that has less pressure, so this will shift right. If we add helium without changing the volume, nothing in our reaction changes actually, because helium is not part of our reaction, so this would be no shift. Okay, so try these out on your own. Send me any questions that you may have on these if this doesn't make sense. We're not going to focus a lot on this because I know a lot of you have seen it. We just sort of need this background information for things that we're going to do in the future. Okay, last thing of this video is we're going to cover notes 3. On the back of your periodic table, you will see all the pH calculations in the acids and bases unit, and we want to be able to do these fairly quickly. So how I always think about it is we need to know that pH and pOH add to be 14. Okay. To get H plus, we'll take 10 to the minus pH. Or to get OH minus, we'll take 10 to the power of minus pOH. And this is because pH is equal to negative log of H plus, and depending on where you're at in math, you may have learned that log is base 10, so that's where the 10 comes from. So again, I'm going to do probably 3 or 4 of these, and then I'll leave the rest of them for you to do and check with the key that is online. Okay, so my gut says get to pH as soon as you can, and then you can get everything from pH. pH and pOH are really nice to work with, where H plus and OH minus are a little bit more tedious to work with. So I already have pH in this first one. We'll call this number 1. And in number 1, I've got 11.93 as the pH, so I'll take 14 minus 11.93. And when I do that, I get 2.07. Now, to get H plus, I'm going to take 10 to the minus pH, so this is going to be 10 to the minus 11.93. And when I plug that into my calculator, I get 1.17 times 10 to the minus 12 molar. Okay, brackets mean molarity. I know we haven't used molarity all that much, but molarity will come back and be important. With hydroxide, we have 10 to the minus pOH. This will be 10 to the minus 2.07, which is 8.51 times 10 to the minus 3rd molar. pH is greater than 7, and like we said on the very first page of these notes, when the pH is greater than 7, this will be basic. Okay, so in number 2 here, I have my hydrogen ion concentration. The first thing I'd like to do is get to pH. So pH equals minus log of H plus, which is 3.45 times 10 to the minus 5. I know some of you can do this without a calculator, so you're welcome to do that. But when I plug this into my calculator, I get 4.46. To get pOH, I'm going to take 14 minus 4.46, and I'm going to get 9.54. To get OH minus, I'm going to take 10 to the minus pOH, and I get 10 to the minus 9.54, which is 2.88 times 10 to the minus 10 molar. This pH is less than 7, so this would be considered acidic. If we have a neutral pH, we will be pH of 7, because pH and pOH add up to be 14, this will be 7. You might be able to do this in your head, but this will be 1 times 10 to the minus 7, and this will also be 1 times 10 to the minus 7. Okay, so go ahead and try out the rest of these and check with the key online.